Kennedy, Vice President of Sales and Marketing for Mazak Corporation, and I have the pleasure of introducing our final speaker in our Discover series of speaking engagements. And our speaker this morning is Tim Shinbara. He's the Chief Technology Officer for the AMT, the Association for Manufacturing Technology. And Tim has been with AMT since 2012. He's been through many economic cycles in manufacturing. And he has corporate responsibility for research, discovery, and standards with AMT. Tim is a U.S. Navy veteran and has supported legislative and policy development for manufacturing at all levels. Most recently as a congressional fellow, representing manufacturing for the office of Senator Marco Rubio. Tim is in all stats and ideas. He started off as a manufacturing engineer at Northrop Grumman and worked as a project manager in R&D and a site lead for manufacturing technology development. Tim is with us today to talk about how digital technologies can help shops transcend production bottlenecks to increase productivity. Digital twins can help close gaps and speed complex manufacturing tasks. Now, let's please welcome Tim Shinbara.
Good morning, everybody. It's interesting at AMT because we have a unique role. We're sort of Switzerland. Everybody still talks to us. When I was with Northrop Grumman, I could talk quite a bit with partners, but I couldn't talk about everything with everybody. And what that did for me coming to AMT was give a broader purview into what is happening in our manufacturing technology space. So for me, it's the duties that Greg talked about was what is happening in the research areas within universities or research institutes. What's happening globally? What does that mean for that economy? What does that mean for the global economy? So there's a lot of this, if you will, techno-economic perspective, and AMT gets a chance to either first observe, if not help impact. So a lot of the times we also sit on some executive committees and steering committees for example, the Manufacturing USA Institutes. American Makes is one of the more prominent ones that we've done most of our work with. But it affords us this perspective that not everyone gets. So part of my duty, fiduciary duty for the association is to convey this information as clearly and as usefully as I can. So we're talking today about digital twins. We'll get into some of those definitions and what that means in a little bit. But oftentimes when we hear those phrases that are above the headlines, that's not for me, it's too complicated, I need so-and-so expertise. And while it's somewhat true, it's not always true. So part of my job today is to show where we see the value and the usefulness for this particular technology lane called digital twins. This is my second time back through Discover, so I appreciate being invited back. The Mazak family has been welcoming. We were on the floor and we were talking, Greg was talking about how much Mazak is like a family with their partnerships and within their companies. I do want to say a great shout out and thank you to Bridget and Becky and Katie for getting everything on the logistics side of this event done well. It was easy for us to come, and it was actually just a beautiful thing to see out there on the Technology Center floor. All things come together, so thank you for that. Getting into more of this presentation now, I do want to talk a little bit about what we do at AMT as it relates. So under the AMT umbrella, we own and operate the MT Connect Institute. It's its own standalone 501c6. It's a standards development organization, SDO, and it's accredited by the ANSI, the American National Standards Institute. So we're an accredited body that produces this standard that we're going to talk about with its context here today. My name's listed here. You can scan the QR code for my LinkedIn. Sharb Singh is the one below me. He is our Director for Systems Engineering. So when we start to talk about words like information models, semantic dictionary, implementation, Sharb's your guy to go talk to real quick first. I can direct you to him or to others, but he does this day in and day out, working implementation challenges through and helping to build a business case for someone who might want to use technology to solve a business problem. So he knows those bits and bytes for the IT/OT. We're going to quickly go through a little bit of some background information I think is both useful and necessary around model-based enterprise, what that means to us in manufacturing. We're going to hit a little bit on the digital twin use cases. So as we build this story today, the main goal for me is to give enough information so that you can take something back to the shop or back to your people that says, these are the types of business problems we want to solve, this is the type of language I think we want to include, and you know the next step to go out of this room to help solve some of that stuff. From AMT's perspective that I recently had just shared, there are 5 trends that we're seeing right now that I consider broad trends. Make sure you guys can see too. 2 of them, space and bio and pharma, are more application space, meaning the work and the development and the trend is happening in the location of space or in the domain of bio and pharma. And there's a lot of enabling technologies that will go throughout all of these, but these are probably the most explicit for an application space. 2 of them, electrification and automation, I would categorize as more process space. So these are things happening to enable other major events and phenomena in a factory for us. But what I really want to highlight today is the digitalization. It's the most fundamental, meaning it has the opportunity to impact the most number of facets of your diamond, if you will. It also is the most necessary to transfer data in our modern world, secure that data, and do useful things with that data, again, back in our modern world with our tools and approaches. It's always helpful to kind of level set, so this is not an academic exercise, though there's plenty of academics doing some work in this space, but it is useful for us to start here. We're not going to walk word through word for all this stuff, but what I do want to highlight is this business environment. When you think model-based enterprise, it's this business environment that effectively is represented by digital data. It's much more than that, but let's just start there. So you could say, if I modeled this thing and it's in digital or virtual space, you're starting to play in a model-based enterprise. So that's an explicit way to look at it, and ASME does another job when it refers to it within another set of standards for this model organization practices. And I just want to highlight what's bolded. This particular standard up top, the Y14.47, is intended to be the foundation for the design development efforts. It establishes a framework for organizing a 3-dimensional model and other associated information for what? To convey a product definition that enables an MBE. So you're starting to get a little bit of sense of what a model-based enterprise smells like. We may not know exactly what it looks like or develop one, but we're starting to get a sense of the first step is take reality, make it virtual. The next step is understand what that means in my own language. And there are plenty of working groups and standards organizations that are just doing work in the model-based enterprise. But for us today, this is our sandbox. This is going to be the world we're going to talk through. This is the ecosystem we're going to live in. It's the model-based enterprise. And hopefully by the end of this, we'll either be convinced or not convinced that it's useful for us in manufacturing. The next definition, so if the model-based enterprise is our ecosystem, the next thing we want to talk about is really specifically the digital twin. I think we all probably 95% can come to a useful digital twin definition. There are a few that are floating out there. There's not one that rules all. But effectively, I've highlighted a few things. Back in 2017, Greaves and John Vickers came out with this first, I think officially first coining it, or at least publishing the phrase digital twin. And they start talking from the micro to the macro level and all the information about it. But one of the things that I really love is what the Digital Twin Consortium says about a digital twin. Not only is it the virtual representation of real-world entities and processes, it gets down by here. It's useful because you can grab information at a certain level, fidelity, and at a certain sequence or frequency. So I need to know about my physical thing at a certain time interval, and I need to know a certain level of detailed information about that entity. That's when you start to bridge from a model to a digital twin. And for us, I have a guest researcher position right now at NIST, the National Institute for Standards and Technology, and my sole role is to be an industry liaison about digital twin and the usefulness of it. What is useful about a digital twin? This isn't an academic exercise of defining it. So the next 2 points were critical for me. You only get into the business of having a digital twin if you want to optimize some type of decision on your factory floor. And not only that, each implementation is a little bit different. And it's not just the make and model of equipment, it's what that make and model of equipment has experienced over its own life. It's not the same as it was when it was first bought off and commissioned on the shop floor 5 years from now, or even 2 weeks from now, depending on what parts you've done. So there's this tailored use case that now says there's a digital twin, it lives in a model-based enterprise, and it's specific and intended for a very explicit reason. And the other thing about it is it has to be built on data, and that data is guided by domain knowledge. So the human is a part of this equation. This is not something that's fully autonomous. We push a button and we walk away and we think everything is great. There still needs to be the human intuition, the human experience about what is useful, what is good, and what is not. So while we do everything we can to incorporate technology to not do the things that we humans are poor at, we cannot lose that domain knowledge. In our standards world, when we talk about domain knowledge, we're talking about, for us, MT Connect serves the domain of discrete manufacturing technology. There's other standards we'll talk about later that serve, say, HVAC or buildings and controls types of domain technology. There's continuous manufacturing, then there's textiles, there's electronics, there's surface mounted. You get where I'm going with all this. All of those particular suites of technologies are their own domain. So these digital twins have a useful nature when they're tailored for a use case, and you have someone that understands the process being a part of that cycle. Now digital twins start to become a little bit more useful for us. In the days of MT Connect, the early days, so this is, by the way, we published the first version of our standard in 2007, if I remember correctly. And for the longest time, it was a machine tool standard, and rightly so. That was the largest portion of the manufacturing technology pie that we felt needed to be connected for data to be collected and to do something with it. So we spent a lot of time worrying about how you get data off the physical machine, instrumentation, sensors, so on and so forth. And then the MT Connect part of it. How do you then structure that data that's going to allow us to understand what we just observed or collected? And then how do you contextualize it? Again, that domain knowledge. What does it mean that my feeds and speeds have produced some frequency of vibration at this particular feature? Is that good or bad? Can we improve it? Do we need to back it off? So those first 3 steps, going from physical to observed to actionable data, was really where MT Connect stayed for the longest time. And we'll always have that, by the way. You know, fundamentally, MT Connect is an information model and semantic dictionary. Information model that structures the data, semantic dictionary defines, gives it context to that data. But what's happened, I'll say recently, is let's call it 5 years-ish. This other side of the world that was not just simulation. They were trying to understand automation. They were trying to understand quicker integrations. They were trying to understand, from an industrial engineer's perspective, what do we optimize next? And we started to realize this predict and prescribe, this virtual data, was starting to come back towards us in the physical world. And the computer scientists and the folks who hadn't sat on a production floor, the IT part of IT/OT, the IT part, felt like they had great models. But what they quickly realized, and you'll see this on any AI or ML blog or report, that model is no good unless it's been trained well. So they started going, well, what happens if we can get better data in? And so we started to move from collecting the data, which is typical, traditional MT Connect standard and some other standards related world, to do things like monitoring and dashboards, to getting this generated data that was predicted. And so the prediction is useful only if it helps us on a particular process that we wanted to optimize. And what we realized was the nexus of that generated data and that collected data, when they talked to one another and fed one another, became the nexus for the digital twin. So in my mind, when you go from a CAD model to simulation, all you've really done is done some better guesswork. When you start to move from simulation digital to a digital twin, the criteria in my mind is you have real data coming back to inform that model. And then what you want over time is that right screen to tighten. You want all of your predictive data points to be in a very narrow band because you know exactly what this thing's going to do given the circumstances. And all you're doing on the collected data side is giving it the real as is circumstance. So this is sort of how we begin to think about digital twins. We start thinking about digital twins as not just being a virtual thing, not just being a quick visual to help my customers understand the layout, to walk around and navigate the floor. Maybe it's useful to get operations and management involved to see about layout and process scheduling and MES related things. But the digital twin really becomes useful when you start to understand how the real world is impacting your part. And all you really care about is timing and quality. I want to know when it's going to be done, and I want to know that it's going to be done well. Everything else almost is noise to some extent. We have to do all that stuff to make sure we have the time right and the quality correct. But all of this really becomes useful. We have the equipment and the technology feeding us this information so that it's doing a lot of the work that we humans, getting down with probes and all this stuff, don't do well at and certainly can't scale. Besides being a complete eye chart and some Industry 4.0 bingo sheet, don't let this get a hold of you too much. I think this chart is really useful for a couple of reasons. This is from Deloitte, and you can go find it on one of their reports. One of the takeaways when I talk to corporate leadership or senior management is they're quick to say, go make a digital twin. Go integrate these pieces of equipment and this technology. You have a very high level, and that's not the fault. That's just, it is what it is. One of the reasons I like this chart is it conveys the complicated nature of playing in this Industry 4.0 kind of world, the smart manufacturing, IoT kind of world. We're nowhere near the plug and play that we would be for, say, printers and adding devices to your router and all this stuff. We're getting there, but we're not fully there. So part of the value of this chart is to say to senior management and corporate, continue to place the bar high, but do it with some grace and do it with some forgiveness, because there's a lot of stuff that has to happen to make that one business statement true. And we'll see a lot more of that on the use cases that we're going to talk about here in a little bit. But let me walk you through this, because there are some key, the second part is a framework for our own selves today. You can look at this more like a column. Right? So we're going to talk about this in 3 distinct columns. This first column, they all have digital twins of some nature up top. So the digital twin, by the way, can be of a part. That's pretty straightforward. People think about that a lot. But it can also be a process, planning or production. It can be of maintenance. What do I do if then statements, or to sustain that part or assembly out in production in the real world. And part of that twin is required to have a system and a design model up front. System model, how's this whole thing gonna work? So we can talk about our model-based enterprise, but it's even more narrow than that. It's about the system, your factory, your processes. And the design starts to get to the part, or the assembly that you're gonna get into. All of these things in modern day, I'll say, have digital files. So there's a way that it has been digitized, and that digitalization in general begins this continuity of a digital thread. So what's a digital thread? No more than a piece of a discrete piece of data that's digital and can be either encompassed into or a part of the next step. We don't lose it, in other words. So digital threads will feed a digital twin the real data that is instrumented in coming off of these types of either planning processes or physical data. We'll stick with the planning process right now. These things have words like systems engineering and model-based definition, and these are just examples. As you move more towards our world, I'll say our day-to-day world as far as percentage of time spent, it is in our factories. And it's about the sourcing and the building after we have the plan. And it's all of our incoming bill of goods, materials, and what we're gonna do. This process model, by the way, is precisely where NT Connect sits. So this is data coming off of equipment that needs to be structured in some context so that it's useful for other things. And as you go down this, you see we get more and more digital thread information that has to be concatenated with the previous digital thread information. So now we're building an aggregate of information. And the third part is that service twin. And we start to get into sustainment and all these other things. This only becomes useful, digital twin, only becomes useful when all of these bits of information are a part of a digital thread, can interoperate with other digital threads, and eventually come back around to feed that next model better information, so that when we start our next iteration, we're a little bit smarter and a little bit better than the next time. That's a real-time view of this. Sometimes it's a little bit more historical. We do a route, or we do a batch, we look at it, we make some changes, we run the second batch. But this kind of a model is a good representation of what a model-based enterprise looks like. And if I just pick out this one process model and tell you that in the process model, there's one domain called discrete manufacturing technology. The one information model for that is MT Connect. You can quickly think about, well, how many other domains reside in process model that I haven't described yet, or that I'm gonna have to interact with or know something about. And by the way, that's just the process model, times the planning model, times the execution model, times the design. This world of model-based enterprise becomes exponential very, very quickly. This is very hard to keep up with from a technology standpoint, especially if you're handwriting out standards and trying to guess what's gonna be the next piece of information that's needed from industry. There's a whole reason why the model-based enterprise is not only useful but necessary because of the tools we need to scale things like standards, not just development. We're gonna talk about layers of harmonization. So again, this is not about a test, an eye chart. This is about putting gravity behind the statement that model-based enterprises, smart factories, these things are not easy. And I think a good way to describe this is the difference between complicated and complex. Complicated the system has a lot of elements, but each node and each element is well known. We can calculate, but you just have to do the calculus, if you will, on the rest of it, but you get an answer, and you always get the answer. That's complicated. Complex is the same system with nodes and elements that are unknown, or they impact things that we can't control. Now, every time I put an input, the same input, I get all kinds of, not just different, I just get all kinds of output. That's a complex scenario. Complexity is a little bit harder to tame, to kind of borrow Maya's tagline. But complicated, we can deal with. Complicated, that's the reason they use that word in watchmaking, in mechanical watchmaking. There are complications, we know how they work, we know how to put them together. That's the world that standards are starting to work in and also provide for us in industry. A known commodity in that element and node world that when we run them all together, we get the same answer from the same input over and over and over again. So I've alluded to it a little bit. We've been developing the MT Connect standard since 2007. It was 2021, I believe, was the first time we did not have the nominal standard be a paper document in a PDF and have fingers and people typing away trying to get this standard developed. There's a difference now though, in our modern world. So we have digital tools and we have approaches like systems engineering that are making a lot of that kind of work more efficient and effective, not just on a factory floor, but even in rooms like an SDO. And just a few things I want to highlight here, on traditional standards. None of these are going to be surprising. What I do want to highlight is the last two. The prone to error and duplication. Think about copy editing just on a blog or a paper you're publishing. And implementation. Right now on a paper document, there still leaves plenty of room of interpretation of what that should look like in implementation. What happens with that, we end up with all sorts of implementation challenges because it doesn't look like what the standard intended it to look like. And then when people are trying to take what they think standardized data, and do something downstream with it, it's not the same as they thought because somehow, some way, the interpretation has lost part of the accuracy of what the standard intended. This has been a real issue. And I do, not only being at Mazak, but I do need to tip my hat to Mazak. And I'm not sure if this is a function of their early support and adoption of MT Connect, so they've had a long time to work in this space, or if it's just par excellence or whatever it might be. Their implementations have been some of the best referenced implementations that we've heard back in the MT Connect Institute. So what does that mean to have a good implementation? It means it's consistent, it's reliable, it's quality, it's what the standard intended. And that meant, so we had, at that time, Neil DeRosier was doing a ton of work in that space for us. So there is something to be said about little life between the Standards Development Committee and the actual implementation on a Mazak. But there is something about having to manage all of that latitude of the interpretation. So we were struggling in the traditional world of trying to develop these standards more manually. And over time, not overnight, over time, these model-based standards have started to emerge. So number one, there's more people who understand this in the industry, not about discrete technology, but about, or manufacturing technology, but about how to develop standards in general in a systems engineering type of world. So these are a few of the benefits that we have, but one of the key things for us, when you start to model data, you can do so in a manner that includes and represents constraints and relationships. That's sort of step one. This data type means this thing. It really has a range of usefulness, or at least of reliable data format or type. And you can test that to make sure what's coming off your equipment is true. But also the relationship. So as you start to see how tool holder as a data format, as a data information model, how a tool holder relates to the tool, which relates to the workpiece, which relates to the work holding, which relates to the machine, which relates to the... These types of things, this parent-child relationship, are very critical when you start to think about how you want to use data. The information models built this way make that so much easier and so much more effective for us in the development world. But besides those two things, one of the biggest functional benefits is this line here. In addition to all that information that I just talked about, there is a whole different world now of behaviors. So I can have, the same way I'd have design intent, I can also have behavioral intent. And I can think about what should this machine, part, process actually be doing? How should it behave? And when I see things that are out of line, red flags, out of tolerance, you can flag them much easier in these model-based standards world. And if you're talking about behavior, if you work in systems engineering world, you might have come across the word ontology, and that's a whole other space we're not going to get into today. It's different than information modeling, but the deal with ontologies is how all these things are not only structured and defined, but how do they relate and how do they behave, and not just within their own domain now. So go back to that Deloitte picture. MT Connect, discrete manufacturing technology, one domain amongst what could be thousands. How do those information models relate at an ontological level with other domain models and other requirements and other behaviors? This is a huge step for us in the modeling world, or at least in the model-based standards world, because the behavior is what allows us to do more for business challenges than just trying to discretely figure out X plus Y plus Z is this. This is a lot more iterative, and it's a lot more business language related. It's also a lot more complicated to deal in ontological models. The last couple of things I'll just say about model-based standards, and we'll move on. There are obviously just some straightforward technical benefits for being in the model-based world instead of a paper handwritten world. Automating the interpretation, so this is machine readable kind of stuff. This isn't me trying to read a sentence and think what the intent is. And also the harmonization. Today, harmonization amongst standards that are paper-based is a lot of folks in a room trying to agree on terms, much like the normal standards committee would do its work. And it's slow, and it's argumentative, and it's not a good argumentative, and we end up being behind what industry needs. Models don't think that way, per se. They know the truth, they know what it looks like to extend for scalability and enterprise level stuff. They can harmonize things if they're personified. Models can harmonize much easier, much quicker than any of us can in the human world, especially when our output is a document. And again, I want to take you back to the Deloitte picture. Think about how much standards harmonization must take place to get just a factory with different processes and equipment to do business things that you want it to do. I've assumed a lot with MT Connect. I do want to hit pause just for a second. It's the only chart really on MT Connect. It does two things. It defines the data and it structures it for us, and not for all things for the manufacturing technology world. That means equipment, it can be material. We are moving into parts and processes, but fundamentally, this is what MT Connect does. It provides that first level of interoperability for your data. So we generally talk about proprietary languages. If you call on O-N, capital O, capital N, that's actually different than a lowercase o-n in machine language. So how do you normalize that language so that it's useful for people either collecting data from a machine, or if you're building on a dashboard or doing some other kind of app? You always want to know what language and what the meaning is. So that's what MT Connect is in its most fundamental state. And like I just said, when we moved to, this is 2.0 was the reason it was 2.0 is because we moved from a paper-based to a model-based standard. For all the reasons I had just mentioned, scaling interoperability, harmonizing with other standards, particularly, hopefully, model-based standards. Scaling, not just from one equipment or a cost center or a cell, but to a whole factory, maybe not just one factory, multiple factories. And then being able to slice that intelligence by process or by location or by time. All these things happen with many different standards. So you can't get, again, back to your business problem, you can't get the full business picture without using multiple standards, not just multiple, it's several. In some cases it could be dozens, depends on what you're trying to do. But this is why it mattered to us at MT Connect and at AMT to move from this paper-based standard into the systems engineering world and use SysML to produce and represent the standard. And it is now the nominal. So the one true single source is the SysML model for MT Connect. And what we've realized is it was not only useful within our discrete manufacturing world, we've had others. So we weren't the first in all things manufacturing or even industry. We were probably third or fourth. We were certainly the first in the manufacturing, discrete manufacturing space to move to model-based. From our lessons learned, we're now talking to multiple domains about how we model, not necessarily about our data and our context, but how in the world did you model, and what were your boundaries and your guidelines as you're building out both the model and the standard itself. There are some things that we've been going through in industry in general, and then I'm going to bring it down a little bit to practical with some use cases to round out our time. I am going to take this moment coming off of EMO just to clarify a few things. OPC Unified Architecture, UA, is its own beast. You can think of a piping transport protocol. It does more than just the transport layer now, though, so I don't think you recognize that, but it's always been reliant and dependent on the context of the data going through the pipe. So you can think of this as the piping analogy itself. It is the pipe, it defines the diameters, the pressures of what fluid might go through, but it doesn't tell you what fluid is going through. MT Connect and domains like MT Connect would go tell someone what fluid is going through that piping process, following the rules of the OPC, transport layer, and all the other stuff. But it doesn't know anything about the stuff going through it. So we were actually the first. Many people didn't know this. We were the first companion spec for OPC UA. It wasn't that useful because it was just a few terms, but it was the first. And what we realized is in the world of standards, you can have two publications, well, three. You can have the standard itself, then you can have a reference standard, and then you can have a companion spec. And I will show it practically in a moment, but the companion specs are when standards work with other standards for a multitude of reasons. That's what we were doing with OPC UA. So the argument was a false argument to say OPC UA or MT Connect. That's apples and oranges. What's more important to say is what context, what domain are you using with your OPC UA implementation? Now recently, this is the moment for clarification, BDWs, this is the AMT for Germany, had produced their own companion spec to OPC UA, which is just machine tools, and it covered a few of the data items. We did rough math. I think it was not less than 10% of the data items we had already covered in MT Connect and had been for a long time. That's not to knock BDW. We are working now to make sure there's only one companion spec for UA, but the question to ask yourself is, what information do you need to make a business decision, and how are you getting the data from the floor to wherever you need to make that decision? We at MT Connect, realizing MT Connect was never meant to be everything. There is no single standard answer for this. We have built the model so that it's interoperable not just with other data, but with other models and other domains. So we've done that also with Spark+B. For folks who are in the MQTT world, and I'll stop with all the technical jargon, because if you're not in that world, it's completely annoying. There's other reasons why you want the MT Connect information model in domains that are much more lightweight. OPC UA is a pretty heavyweight implementation. MQTT is a very lightweight implementation to get a message from a place to a place. So Sparkplug B is their specs to how the communication occurs. We have a companion spec in MT Connect to work with Sparkplug B. And that's just two of some recent ones. We've done this with quality information format, or framework format, QIF for metrology, and a whole host of others. You'll see a little bit of those pop up in a moment. But our biggest thing is, as a concern and a risk in this world from an SDO's perspective, is once you start getting more domains and more interoperability, it's that validation concern that really comes up. So if you're an operations manager and you're thinking about approving an implementation, you have to start thinking about, how do I prove? How does this integrator tell me that what has actually been implemented, either at the machine or at our controls level, is what we've asked for them to do. So you need to make sure you've got validation as a part of your statement of work when you're going into some of these implementations. This is a good pictorial representation of the reference and companion spec. So for example, MT Connect, left side here, this is the discrete manufacturing technology domain. Things we do all day long, machine tools, robotics, work holding, end effectors, Obviously, there's tools that go in here, and the ISO 13399 spec preceded MT Connect. It's been around for a while. So we didn't go reinvent any wheel. We didn't go talk to ISO just to harmonize and what, we just take it. This is called a reference spec. So if you're a programmer, or if you're an implementer or integrator, you should always look to see what currently exists. You're gonna have a basket of goods, and you gotta figure out how that basket of goods becomes a meal at some point today. But this is a reference spec. We just point to this. Now as we go up, we start to understand it's not about reference specs anymore. This is about companionship, if you will. So again, the transport analogy still holds. The context of all the stuff that's happening here just gets piped into this, and I'm gonna state the transport protocol there. It just gets piped into this thing that already exists. So it's a companion to this, where this is referencing something very specific. So you kind of see the world in which we live in. I put BACnet, that's the Buildings and Control Network standard, beside it, just to give you a sense of there are other domains that would also use OPC UA. And OPC UA is not the only transport layer protocol. There are many others that could be utilized as well. Certainly there's a lot happening in EU and in Germany on UA. A lot of that's from the government, so I don't want to, but the industry will have to figure out how they want to get their data all the way up to do whatever it is they want it to do. So up to this point, we sort of built up a case for what's the world we live in. It's called the model-based enterprise for today. If we're in that ecosystem and in that world, what are our tools? What's our vocabulary? It's about this digitalization. It's about a digital thread, a piece of information coming up with something we have interest in. Well, let's keep all those digital threads together, and eventually that will feed what we'll call the digital twin today. So now we're starting to understand a little bit of how all this might work. The next few charts, I want to stop and kind of walk you through some implementations. So I think it was in 2020, 2021, 2020, we had a group of MT Connect Standard Committee members work with an ISO group and demonstrated in their facilities some of these applications of digital twin. I think these will, all the charts will be available, and I believe this is being recorded too, so you can check this later. This is a great YouTube video, so if you have an hour, it takes about an hour, to go through the 3 implementations in detail, you will see them. And for today, I've captured Boeing, one led by Lockheed Martin, and one led by Sandvik. And we're going to walk through a little bit of some of these implementations. I like them, and then I don't like them. I like them because it's one of the first practical steps of this digital twin having some context and usefulness for us in manufacturing. Okay, I see why we want to do it. I don't like them because it was done very manual, because we did not use any of the model-based standards. In fact, the only one close would have been MT Connect, and we weren't ready at that time yet. So this is all a bunch of manual, laborious work trying to interpret, make it fit in the system, and work with other things. The standards helped because we didn't have to start from scratch, but it certainly wasn't as optimized as we'd like to show it in the future. A little bit of framework, because you're going to see some of these words in the graphics that I have after this. So the ISO 23247 is a huge standard. but it's about model-based enterprise and has a whole section on digital twinning, using that as a verb. This is one of the more useful charts because this is the language that our use cases used. But this gives you a functional view of where data is coming from, where it's going to, why it's useful, and at what point it becomes a closed loop system and comes back. So for us today, I'm just going to use a few different words on the left side. So observe. These are your sensors, the instrumented sensors on your equipment. It's emitting signals of some sort. We can discern that somehow. That's happening down here at our OME, Observable Manufacturing Elements. Machine tools, robots, grinders, homing devices, all that kind of manufacturing technology stuff. That data then gets collected at what we call the device communication entity. You'll see the acronym DCD, data collection, data control entity, DCDCE. You'll see that. That's this layer. This is where all that data is starting to reside. So for us, this is part where MT Connect starts at an adapter level. So I'm getting the information, I'm starting to structure it. I'm starting to put some definition behind it to give me some insight, not insight, just some intel on what it is. So that's happening here. After we collect, this is, we call it the core entity for the use cases. The core is only because our focus is on digital twins. So this is where the digital twin of either part or process are residing for these use cases. We won't go into all these boxes. That's where the model is sitting. And then we start to get to the useful part. So up at the application layer, for those in IT, I'm talking about the OSI model. Application, the most useful, meaning the human is interacting with the application layer. I'm seeing colors, I'm seeing numbers, I know what to do with it, or the system knows what to go feed that to somewhere else. This learn and act is what we might call training a model. It also might be called optimization. It's taking what actually happened, comparing it to the as designed, understanding the delta, there will always be a delta, and then more importantly, what's of interest to us? Are there boundary conditions? Or were there other red flags that occurred that we need to know about? That's where that's all happening up here at our user entity. So observe, collect, get the data, collect that data, structure it, feed it into something that is functional for us, in this case, digital twins, and then become useful. Let's learn and act on that knowledge up here at the application layer at the user entity. I could talk all day, so I gotta make sure we're doing okay. Get close, all right. These are the three. So Boeing started out, they had a monolithic robotic solution. It was a bottleneck by volume of parts because you can only have one part on it at one time. If anything in the as produced condition was off, they had to add new programs to go figure out what was going on with that particular part, it's a wing part. So they, Boeing, have this phrase called condition of assembly, COA. Their goal was, can we attain dynamic scheduling? So again, today it's very static. We're gonna run this part, we're gonna run this part file, and it's gonna hit these specs and inspection or not. Can we drive dynamic scheduling by knowing more and collecting and connecting the data from the condition of assembly, that's as is for Boeing, to help us with that? And their business question is, what's the impact on the schedule? So much like Deloitte, we're not gonna go through all this. I just wanna highlight a few quick things. Everything happening between the supervisory control, the user entity, and the core entity are solely standards information. So what was happening? We had the model, the as designed, being fed down into where the data was going to be collected for later for evaluations. And that interaction at the models to the translator levels, well I should say translator, the DCDE level, was informing the as designed. What we found is using state streams. So state just means you know what it's supposed to do, back to behavior. It's a light switch, is it on or off? It's a pump, is it pressurized or not, right? That's the kind of statefulness we're thinking about. The state stream data was gonna come up, feed into our models, and tell us what we should adjust, if anything to adjust. This is Boeing, right? So they were trying to move away from this monolithic, and they had roughly 20 or so, not too many, 12 or so robots, smaller, individualized, that could be programmed differently. So they were getting that understanding, so they learned and they acted and then assigned a new sequence of instructions back to the machines doing that work. So this happened when the as-is condition was off, out of spec of the as-design, and they needed to do either more processes or not one process at all. So there are a lot of benefits to this. I'm just gonna highlight a couple here, but all this stuff can happen on one infrastructure. We start living in a model-based enterprise world. There are the standards that enable all this are on the right-hand side. Of course, process monitoring for MT Connect, some other things. The part itself. So how do you get that as-is data downstream to something that can use it for usefulness? And the normal things we think about with real-time monitoring, and then the process itself. It enabled Boeing to make dynamic scheduling and process modification on the fly. They effectively learned and manufactured on the fly. All enabled by the standards, which all had to be harmonized. That's the deepest I'll go into any of these, because the last two are fairly quick. Similar approach, different problem. Multiple materials stacked up for Lockheed. They had to put a fastener through it. They had carbon fiber, aluminum, titanium. There's material tolerances, min-max on each of those. You go to the higher end of any of those tolerances, all of a sudden you're either out of spec or you're requiring a very long fastener. The length of that fastener matters because there's thousands of them, and that's a lot of weight for an aircraft. They were interested in how do you get the quality data to describe that observable measurement so that they can minimize the length of their fastener, because their business question was, why are some of these larger than others? We won't do much here except talk about the model, the as-designed feeding into the commands for this inspection. And in this case, the execution and the communication was all about just measurements, not state stuff, just strict data. That all get fed back up, and this was happening in 2 different places, in New York and then down at Fort Worth in Texas. This is the last one. So Sandvik had an automated detection analysis and resolution issue. They were having machines cut differently almost every time for some reason. So they were curious about when do machining changes impact their design tolerances. Similar setup. This now, though, has everything that we just talked about all included. They have not just the commands and the state nature, they also had inspection data and instructions data, and all this stuff is happening in one time. Again, we won't go through all this, but total standards happening between the supervisory control and the core entity. So the user entity and the core entity, all relying on these standards to make sure the data was discernible, consistent, and understandable, and ultimately getting back up to the user entity role to be useful. Right? So any one of these, by the way, is an hour-long conversation on a workshop. I just am trying to give you some sense of what is usefulness when we talk about digital twins, and who's really doing it? Is it just universities? The answer is no. And while we had names that most people recognize here, there are many other tier 2, tier 3s that are starting to understand at least this process. And so as we look at all this together, my main takeaway is digitalization is not just a term, digital twin is not just a term. We're finding that there is practical usefulness in the factory. And there are different ways with our modern tools and our modern approaches and our modern knowledge about systems engineering specifically, about which we should go tackle these kinds of problems. Standards harmonization, because of all the different ways we could collect data, all the different ways that native data is produced, you cannot scale this stuff without standards. And it's not one standard. You can't do that without having harmonization amongst those standards. For us, when we look at the model-based enterprise, this viewpoint seems to be the only way we're gonna do production well, intelligently, sustainably. It's the only way we're gonna have the data we need to make better decisions about those processes. And we certainly think it's not just about the production. If you remember back to the Lloyd picture, it's about the planning, the production, and sustainment. What does this look like in warranty conditions and all these other things? So we at the MT Connect Institute are talking to these other domains because we foresee these kinds of challenging questions being posed to us. And we can't answer them today in the current state, so we're going to continue to develop towards that end. That's the reason for us to go to SysML. We're doing a lot with ontologies in the world of industrial space, so we spend a lot of time, Chief Architects Will Savell spends a lot of time talking to those types of people, trying to keep the main reason, the main motivation for AMT starting anything in this world was to try to keep the U.S. manufacturing staying advanced, the state of manufacturing being advanced. What is it that we're going to foresee that's going to come help the production facilities tomorrow, so we can do something today about it. So with that, that's me and Sharb. Technical questions go to Sharb, easy questions come to me. I am more than happy to take some questions now. I know the agenda has probably got some more tours and stuff coming on, Greg, so I'll leave it up to you. But really appreciate your time. This is so key for me to give you this kind of information, so I appreciate you taking the time out of your busy day for me. Appreciate it.